this lesson. In the previous chapters, we explored the general workflows for managing agricultural waste depending on technologies and breeding systems. Now, we will focus on pre-treatments and treatments, crucial steps for giving agricultural waste a second life. Waste valorization not only reduces the environmental impacts, but also transforms byproducts into valuable resources, such as fertilizers, compost, and renewable energy. This is a key component of the circular economy in agriculture. So today, we are talking about the strategies and technologies for the valorization of agricultural waste. Agricultural waste valorization is essential for sustainable resource management. So in this lesson, we will cover pretreatments, treatments, and their final products. The pretreatments make waste suitable for further use, while treatments like composting, anaerobic digestion, or denitrification turn waste into energy, digestate, or fertilizers. Pretreatments are important to obtain a substrate suitable for the treatment in order to give a new life to the agricultural byproduct. Depending on the nature of the material, a variety of pretreatment methods can be applied. The mechanical pretreatments include chopping, grinding, or shredding, which increase the surface area and improve the microbial access, thus enhancing the degradation rates in biological processes. Thermal pretreatment, heating the biomass, typically between 70 and 150 degrees, to break down cellular structures and promote hydrolysis or fibrous material. Techniques include steam explosion or hydrothermal treatment. Chemical pretreatments, use of acids, alkalis, or oxidizing agents can degrade lignin and improve the accessibility of structural carbohydrates. However, care must be taken to avoid the formation of inhibitory compounds. Finally, we have also biological pretreatments rely on the activity of a specific microorganism or enzymes, such as the lignin-degrading fungi, to initiate the breakdown of complex molecules in a more environmental friendly way, through often slower and more costly. One of the most common and effective forms of pretreatment is the solid-liquid separation, especially relevant in the management of livestock manure, digestate, and liquid residues from agroindustrial processes. So, in the following paragraphs, the most important pretreatment and treatments were discussed. Talking about pretreatments, this figure represents a generally solid liquid separation. First, manure from livestock is collected and stored in a pre-tank to allow it to mature and become more suitable for processing. Next, a pumping system transfers the manure to the separator. The liquid fraction is then stored and later used for agronomic purposes, while the solid fraction can be directed to composting or other forms of treatment. Different technologies are available for solid-liquid separation, including mechanical presses like screw or auger separators, roller separators, vibrating screen, or centrifuges. Among these, screw presses and roller presses are the most widespread due to their favorable balance between performance and operational cost. In the screw press systems, manure is conveyed through a cylindrical filter using a rotating screw, where the liquid passes through fine slits, while the solid is compressed and discharged. The roller press systems instead operated with a rotating drum and pressure rollers that dewater the material, resulting in a less moist solid fraction. The efficiency of separation depends on the physical properties of the input material, especially the total solids content. Higher total solid concentrations lead to better separation outcomes in terms of dry matter and nutrient capture. For example, screw press separators working with cattle manure with total solid above 10% can achieve solid fraction total solid values above 24%, while the separation efficiency for nitrogen and phosphorus can reach 30% or more. Conversely, pig slurry, being more diluted and fine-textured, typically show lower separation efficiencies. The separated solid fraction, aside from direct agronomic use, is an attractive substrate for anaerobic digestion, particularly because it contains a higher concentration of biodegradable organic matter per unit volume compared to raw slurry. For example, solid fraction of cattle manure may contain up to 92% volatile solids relative to total solids, as opposed to 82% in unseparated slurry. This makes them more efficient for biogas production, particularly in co-digestion settings or when transport over long distances is necessary. From a logistical perspective, solid-liquid separation reduces the total volume of material to be handled, stored, and applied, thereby lowering costs associated with labor, machinery wear, and fuel consumption. Moreover, the clarified liquid fraction can be used efficiently in fertigation systems and, under certain conditions, even replace fresh water in livestock facility washdowns, contributing to water conservation. Among treatments, we can find biological or thermochemical and chemical treatments. Talking about biological treatments, we can find composting, which aerobically transform organic residues into nutrient-rich soil amendments, reducing the need for chemical fertilizer. And also we can have the anaerobic digestions and the biogas production that allows for the recovery of energy by converting organic matter into methane-rich gas and digestate, which can also be used as fertilizer. Regarding thermochemical treatments, we can have pyrolysis, a process carried out in absence of oxygen that converts agricultural biomass into biochar, biooil, and syngas, offering potential for carbon sequestration and renewable energy. Finally, we can have chemical treatments such as nitrification, denitrification, a microbial-driven mechanism central to the nitrogen cycling. During nitrification, ammonia is oxidized into nitrate via nitrate by specialized bacteria such as Nitrosomonas and Nitrobacter. And this is followed by denitrification, where nitrate is reduced to nitrogen gas under anoxic conditions by denitrifying bacteria like Pseudomonas and Paracoccus. And this two-step process plays a critical role in removing excess nitrogen from soils and wastewater, thereby mitigating environmental risk such as the eutrophication and or the groundwater contamination. Together, these technologies not only minimize the waste, but also contribute to circular economy models in agriculture. Composting is a biological-driven aerobic process that converts organic agricultural residues such as livestock manure, crop waste, and pruning materials into stable, humified product known as compost. This transformation is facilitated by naturally occurring microorganisms that break down the organic matter into carbon dioxide, water vapor, heat, and nutrient-rich substances, resulting in a material that significantly improves soil structure, fertility, and microbial health. In this figure is reported the workflow of the composting. The composting process is structured into distinct but continuous phases, each dominated by different microbial population and characterized by unique biochemical activities. Before starting the composting process, it is often necessary to include additional materials and carry out pretreatments to ensure an optimal condition for the decomposition. Cellulosic materials such as the wood shavings are important for balancing the organic matter, supporting also the animal and plant health, and ensuring proper porosity together with the achieving the correct carbon-nitrogen ratio. Fertilizers rich in phosphate and potassium can also be added either during heap preparation or directly when distributing and burying the compost. Other additives, including bentonite, that is a silica clay able of retaining water up to 10 times its weight. However, there are also some additives that could be added, such as lime and gypsum, that should be used cautiously, as an excessive amount can alter the conditions needed for a proper organic matter decomposition. We can use microbiological activators such as selected strains of bacteria, fungi, or yeasts because they can help start the composting process, especially for difficult materials that are very rich in lignin. These activators can be spread directly on the litter, thus saving time in heap preparation. However, the best starter is often the compost from the previous year, as it already contains the microorganism essential for breaking down organic matter. Before starting the process, it is also important to do physical pretreatments such as shredding, laceration, or defibration that improve the structure of the biomass because increase the contact surface and activate the microbial metabolism. A proper mixing and homogenization, along with adjusting moisture, either wetting dry material or removing excess water, can help to prevent abnormal or excessive fermentation and to ensure a smooth composting process. The composting process can be divided into three main phases: thermophilic, maturation, and stabilization. Starting with the first phase, the thermophilic phase involves the bacterial oxidation of fats, proteins, and sugar at temperatures above 60 degrees. It typically lasts 1 to 4 weeks. And a continuous turning and aeration ensure homogeneous distribution of aerobic bacteria. So during this phase, the pile must remain at higher 55 degrees for at least 3 days to sanitize the material, to kill pathogens and weed seeds. The activity of microorganisms transform complex compound, and this process ends when the pile no longer heats, despite turning or wetting. Then the second phase. During the maturation phase, fungi and actinomycetes further break down cellulose and lignin, while organic acids are neutralized. A key parameter in this phase include pH, which rises to neutrality, and also we have moisture that is reduced to 35–40%. A proper aeration prevents anaerobic conditions and odor formation. So in this phase, we stabilize the compost, making it safe for use on crops. Then the third phase, the stabilization phase, produce a stable humus. Indicators of completion include the fact that the material resembles soil with a strong, healthy smell, and that sensitive plants such as flower can be grown without damage, confirming that the toxins are gone, and also that the carbon-nitrogen ratio reached 12:15, ensuring a chemical stable product. In this process, temperature, nutrient content, carbon to nitrogen ratio, and moisture are closely interrelated, meaning that an excess or deficiency in one of them will almost always affect the others, with direct consequences on the success of the process. Temperature plays a crucial role in microbial activity, and For an optimal performance, it should generally be maintained between 50 and 60, maximum 65 degrees. The carbon-nitrogen ratio is particularly important, and an ideal balance lies between 25 and 30 units, as it ensures that microorganisms have enough carbon for energy and nitrogen for protein synthesis. Moisture also needs careful control. Under initial condition, it should not exceed 60-70% because an excessive moisture can lead to anaerobic conditions, depriving aerobic microorganisms of oxygen and slowing down the process. From a technological standpoint, composting systems can be broadly categorized into open, enclosed, and in-vessel methods. Open systems, such as window composting, are often used in agricultural settings due to their simplicity and low cost, but require large land areas and a careful weather management. Include systems, which include aerated static piles covered with semi-permeable membranes, offer better control over emission and temperature, of course, but involve higher investment. In-vessel systems are highly controlled environments suited for urban or industrial composting, able of processing large volumes efficiently, while minimizing environmental impacts. Composting's flexibility allows for both decentralized and centralized application. Community level or on-farm composting minimize transportation needs and operational costs, making it accessible for small-scale or peri-urban agriculture. Central facilities, by contrast, can handle higher volumes of organic waste and are often integrated with municipal waste management systems. Composting is recognized not only for its soil enhancing properties, but also for its environmental advantages. Unlike landfilling or incineration, composting diverts organic waste from disposal, thus reducing methane emission from anaerobic decomposition and preserving landfill space. Furthermore, it mineralizes essential nutrients such as nitrogen and phosphorus into plant available forms, allowing compost to serve as a partial or total substitute for mineral fertilizers. Compared to raw manure, compost has a more stable nutrient profile, a lower risk of nutrient leaching, and reduced odors and pathogens, making it a safer and more predictable soil amendment. Agronomically, compost enhances the soil fertility through both direct nutrient supply and improvements in soil physical properties. The slow release of nitrogen in organic forms improves nutrient use efficiency, while organic matter contributes to increased water holding capacity, enhanced soil aggregation, and stimulated biological activity. These benefits are particularly significant in degraded soils, where compost can play a pivotal role in restoration. Moreover, composting supports circular agriculture by recycling nutrients within farming system and reducing reliance on synthetic fertilizer, whose production is energy intensive and reliant on finite resources. Despite these advantages, composting is, of course, not without its challenges. A mismanagement, such as an incorrect carbon-nitrogen ratio, an insufficient aeration, or a poor moisture control, can lead to odor issues, to incomplete decomposition, and, of course, to greenhouse gas emissions, notably by ammonia and nitrous oxide. So, careful monitoring of process parameters, including temperature, oxygen levels, and moisture, as we said before, is essential to ensure optimal outcomes. Additives like biochar or structural bulking agents can further improve compost quality and nutrient retention. Regulatory frameworks in the EU and other regions increasingly recognize composting as a sustainable waste treatment method. These include requirements for pathogen reduction, such as time temperature thresholds, limits on contaminants, such as heavy metals, and standard for product maturity and stability. A compost that meets this standard can be hence safely used in organic and conventional agriculture, landscape restoration, and horticulture. Let's go to anaerobic digestion. This is a biological process that breaks down organic matter, such as food waste or animal manure, in the absence of oxygen, leading to the production of biogas to digest it. As this figure describes, the process requires input, food waste, microorganism, energy, and water. The outputs are biogas and digestate that could be liquid or solid according to the kind of waste employed as input. Manure composition and properties vary significantly across livestock species due to differences in diet, digestion physiology, housing system, and water use. And this variation greatly influence the suitability of manure for anaerobic digestion, composting, and agronomic use in general. This figure describes yield of biogas starting from different manure. The manure of swine achieved the best performance compared other kinds of manure. This is because swine manure is rich in readily biodegradable organic matter, especially proteins, carbohydrates, and lipids, which provide an excellent substrate for anaerobic microorganisms. Its relatively high moisture content and balanced nutrient composition also create favorable conditions for methanogenic bacteria, leading to efficient biogas production. In contrast, cattle manure often contains more fibrous material, such as lignocellulose, which is harder to degrade, while poultry manure may have high nitrogen levels that can inhibit microbial activity if not managed carefully. Sheep and goat manure, being drier, have lower degradability and produce less methane per unit of waste. For this reason, swine manure typically achieves the highest biogas yield among common livestock wastes, making it particularly suitable for anaerobic digestion and renewable energy generation. This process is carried out by a consortium of microorganisms and occurs through four main stages: hydrolysis, acetogenesis, and methanogenesis, as illustrated here in this figure. During hydrolysis, complex organic compounds such as carbohydrates, proteins, and fats are broken into simple molecules like sugars, amino acids, and fatty acids. These simple molecules are then further transformed during acidogenesis and acetogenesis into volatile fatty acids, hydrogen and carbon dioxide. In the final stage, methanogenic archaea convert these intermediates into methane, carbon dioxide, and water, which are the primary components of biogas. Biogas typically consists of 50-70% methane and 30-50% carbon dioxide, making it a valuable renewable energy source that can be used for heating, electricity generation, or as fuel. The scheme in this figure summarizes the general workflow of the anaerobic digestion. It involves a wide network of actors, each playing a critical role in ensuring the efficiency and economic viability of the process. At the foundation of this chain are livestock farmers and agricultural producers. Farmers not only contribute raw material, but also often serve as plant operators or partners in biogas cooperatives, thereby diversifying their income streams and reducing their environmental footprint. The second key actor in the chain is the biogas plant operator or consortium, who oversees the technical and operational aspects of the anaerobic digestion. This stage involves the controlled microbial breakdown of organic material in the absence of oxygen, resulting in the production of biogas and digestate. The digestate could define as the residual material left after the anaerobic digestion of organic substrates. The biogas can be used directly for heating and electricity generation, or can be upgraded to biomethane, a renewable substitute for natural gas, which can be injected into the gas grid or used as a vehicle fuel. Engineering and technology providers play an essential role in supplying and maintaining advanced equipment for pretreatment, such as the liquid-solid separation, digestion, biogas upgrading, and monitoring systems. Innovation in these areas help increase the efficiency, safety, and the scalability of biogas plants. Finally, the local communities benefit directly from the biogas chain. Behind energy supply, biogas plants can help reduce odors, decrease the pathogen loads in manure, and lower the greenhouse gas emissions. In many cases, digestate is returned to agricultural land as a stabilized, odorless fertilizer, completing the circular economy model. The anaerobic digestion takes place in an anaerobic digestion plant. Here, several key components ensure the safe management, treatment, and utilization of biogas. The digester is the central unit of the anaerobic digestion system, a sealed oxygen-free chamber where microorganisms decompose organic matter to produce biogas and digest it. It provides the ideal environmental condition for microbial activity, including a controlled temperature, pH, moisture, and mixing. Digesters are usually cylindrical or dome-shaped structures built in reinforced concrete or steel and designed to maintain airtight conditions to prevent the oxygen entry and the gas leakage. Continuous stirring systems ensure homogeneous mixing of the biomass, while heating systems keep the temperature in the mesophilic 35 to 40 degree or thermophilic 50-55 degree range, depending on the process type. The biogas overpressure valve plays a crucial safety role. It automatically releases gas if the internal pressure of the digester exceeds the safe limits, preventing structural damage and ensuring stable operating conditions. This safety feature is essential for maintaining the integrity of the system and protecting both the equipment and the operators. Inside the digester, the biogas treatment process begins immediately after the gas formation. Here, moisture and impurities such as hydrogen sulfide are partially removed through an internal separation system, reducing corrosion risk and improving the quality of the gas before it moves to external purification stages. After preliminary treatment, the gas can follow two main pathways. First, delivery to the grid, where upgraded biogas, such as the biomethane plant, undergoes final purification and compression to meet natural gas standards. Once injected into the natural gas network, it can be distributed for domestic, industrial, or transport use. Or cogeneration, where raw biogas is burned in a cogeneration unit to simultaneously produce electricity and heat. This heat can be used to maintain the digester's temperature or to supply nearby facilities, while the electricity can be consumed on site or exported to the power grid. Biogas plants can generally be classified into three main types, each with specific technical characteristics and suited to different farm sites and management strategies. Let's start here with the duct-type plug flow system. It requires pre-separation of coarse solids, which are not readily biodegradable with reasonable technical time frames. Only the liquid fraction, so, of the manure is used in this anaerobic process, and the digester has no internal mixing devices. It is suitable for medium to large scale farms aiming to produce biogas primarily for self-consumption, using surplus energy for sale to the grid operator when available. For optimal gas production, the manure must reach the digester as fresh as possible. Therefore, all necessary measures should be taken to rapidly evacuate slurry from animal housing facilities. The manure is first conveyed to a pre-collection tank and then pumped to a separation unit. The solid fraction separated before digestion can hence be composted or used as a soil conditioner. Anaerobic digestion occurs inside the digester through the activity of bacteria that decompose complex molecules into methane, carbon dioxide, water, and hydrogen sulfide. These biological reactions are influenced by several factors such as pH, temperature, and the hydraulic retention time. When the digestion temperature decreases, of course, a longer retention time is required, around 60 days under psychophilic condition and 18-20 days under mesophilic condition. When these parameters are respected, the system can ensure excellent energy yields all the year round. The biogas is collected in the upper part of the digester under a triple membrane gasometric dome. The innermost membrane contains the gas in contact with the slurry. The middle membrane prevents mixing between gas and air, while the outer membrane remains inflated, maintaining pressure stability. The gas is conveyed to a cogeneration unit, where it is combusted to produce electricity and heat. A portion of the heat is reused to maintain the digester temperature. The stabilized and deodorized digestate is then stored in basins until its agronomic reuse. Let's talk about the mixed upflow cylindrical plant. In these systems, raw manure, so liquid and solid fraction, is used directly without prior separation. This because the cylindrical digester is equipped with a propeller-type mixing system that ensures uniform blending of the biomass. The digester is fed daily with fresh slurry, while digested material exits after an average retention time of 20-25 days. It is suitable for farms that aim to manage manure as a single homogeneous substrate and maximize biogas and economic yield. Because all the solid fraction remains in the process, biogas production is significantly increased. However, to work, these systems requires proper pumping equipment to handle the unseparated slurry, more electromechanical components, higher self-consumption of electricity, of course, and additional land availability if nitrogen-rich co-substrates are added, as required by agronomic use regulations. As with the plug flow system, it is essential that the fresh slurry reach the digester quickly. The digested volume can also be divided into two reactors, a primary acidogenic and a secondary methanogenic chamber. This will allow a better control over the biological phases. Then we have the superflow type plant for dense biomass. This type of system treats raw manure and biomass, so liquid plus solid fractions, under high density conditions. It typically consists of two digesters, a primary and a secondary reactor. The primary digester, that is cylindrical in shape, is fitted with a horizontal axis mixer that ensures through blending of manure and biomass. It is continuously fed with fresh material, while partially digested slurry exits after 20-30 days and enters the secondary digester, which also has a mixing system to recover residual biogas. The overall retention time across both reactors is approximately 60 days, so 30-40 days in the secondary digester. This bioreactor is best suited for large livestock or agricultural farms with steady biomass availability through the year, enabling high and stable biogas and electricity production, thereby maximizing the process efficiency. The biogas produced under, of course, anaerobic conditions is collected from the top of the digester under a variable volume spherical dome. The recovered gas is then balanced, cooled, dehumidified, filtered, and sent to the cogeneration units for the combined production of electricity and heat. Finally, the stabilized and deodorized digestate, either whole or after solid liquid separation, is stored in holding basins awaiting agronomic application. Within the biogas, another important output is the digestate. That is a nutrient-rich material that can serve as a valuable agronomic resource. Indeed, it is considered as an important agricultural byproduct. It is the residual material left after microorganisms have broken down organic matter in the absence of oxygen. Its appearance and texture depend on the type of feedstock and on the specific digestion process, but it generally presents as a moist, dark brown to black material with an earthy or slightly fermented smell. Digestate usually has a semi-liquid consistency, similar to slurry, especially when derived from manure or food waste. In some systems, it can be separated into two fractions. A liquid fraction rich in dissolved nutrients such as nitrogen, potassium, and phosphorus, often used as a liquid fertilizer, and a solid fraction containing more organic matter and fibrous material, which can be composted further or directly applied to the soil as an organic amendment to improve structure and water retention. Chemically, the digestate is stabilized, meaning that most of the easily degradable organic matter has already been converted into biogas. As a result, it emits less odor than raw manure and has a lower pathogen content, making it safer and more sustainable for the agricultural use. However, its management and application require careful consideration according to its physicochemical properties, which vary significantly depending on the feedstock composition, on the operational parameters of the digester, and to any other post-treatment processes applied. So the digestate contains key macronutrients essential for plant growth, including nitrogen in both organic and ammonium forms, phosphorus, potassium, calcium, and magnesium, as well as trace elements such as zinc and copper. The total nitrogen content in digestate ranges broadly, typically between 1.6 and 13 gram kilos of fresh matter, with ammonium nitrogen often accounting for the 40–80% of the total making. And this is readily available for plant uptake. Phosphorus is usually present in inorganic forms, ranging from 2 to 6% of the dry matter, and potassium levels are commonly comparable or slightly higher. Digestate generally has a neutral to alkaline pH from 7.3 to 9, which can affect the nutrient availability and microbial activity in the soil. Heavy metal content, particularly in digestates, derived from animal manure, so they also must be monitored due to potential accumulation in soil over time. And Table 5 summarizes the composition of the digestate. Biomethane is produced by upgrading biogas, which is generated through the anaerobic digestion of organic materials, such as agricultural residues, manure, food waste, and sewage sludge, as we talked before. Biogas primarily consists of methane and carbon dioxide, along with small amounts of impurities like hydrogen sulfide, water vapor, and siloxanes. To obtain biomethane, that is a high purity methane gas suitable for use as a renewable natural gas, the biogas must undergo purification. Common biogas upgrading technologies include the water scrubbing, pressure swing adsorption, chemical absorption, and membrane separation. Water scrubbing uses water under pressure to absorb carbon dioxide and impurities. Pressure swing separator gases under varying pressure cycles. Chemical absorption involves solvents that selectively capture CO2, while membrane separation employs semi-permeable membranes to filter gases based on molecular size. This process removes carbon dioxide and contaminants, resulting in biomethane with a methane content typically above 95%, comparable to fossil natural gas. In the European Union, the biomethane production has been steadily increasing, currently reaching around 3.5 billion cubic meters annually. This amount represents about 10% of the total biogas produced. This expansion supports the European Union's goal for decarbonization, renewable energy uptake, and waste management. Finally, biomethane plays a critical role in reducing greenhouse gas emissions by substituting fossil natural gas in heating, electricity generation, and transport fuels. Additionally, its production helps to valorize agricultural and organic waste, turning potential pollutants into valuable energy and biofertilizer, thus promoting circular economy principle. Beyond composting and biogas, agricultural waste can be valorized through pyrolysis, producing biochar and bio-oil, extraction of valuable compounds such as bioactive molecules, enzymes, and organic acids, and conversion into biofuels, bioplastics, and biofertilizer. This figure can summarize the different thermal treatment of waste management. Pyrolysis is a thermochemical decomposition process that converts organic materials into useful products through the application of heat in the absence of oxygen. It typically occurs at temperatures ranging from 300 to 700 degrees and involves the thermal breakdown of complex molecules into simpler compounds. The primary chemical reactions in pyrolysis are endothermic, meaning they absorb it and include cracking, so breaking long hydrocarbon chains, dehydrogenation, and carbonization. The process yields three main products: biochar, that are solid, bio-oil, that are liquid, and syngas, that of course is a gas. The proportion depends on the operating temperature, the heating rate, and the feedstock characteristics. Biochar, rich in stable carbon, can be used as a soil amendment, improving soil fertility, water retention, and carbon sequestration. Bio-oil, a complex mixture of oxygenated hydrocarbons, can be refined into fuels or chemical precursors, although its high acidity and instability require further processing. And syngas, a mixture of hydrogen, CO, and methane, and small amount of other gases, can be used to generate electricity and heat, or serve as a feedstock for Fischer-Tropsch synthesis to produce liquid fuels. Unlike combustion, pyrolysis avoids direct oxidation, thus minimizing the formation of nitrogen oxide and sulfur oxides. However, a careful control of process parameters is needed to reduce the formation of polycyclic aromatics hydrocarbons and other potentially toxic byproducts. Pyrolysis can treat a wide range of materials, including biomass, sewage sludge, plastics, and tires, making it a promising technology for waste to energy conversion and circular economy strategies. Energy-wise, pyrolysis is energy intensive, but part of the syngas produced can be combusted to meet the system's heat demand, improving the energy efficiency. Integration with renewable heat sources or cogeneration systems can further reduce environmental impacts. For large-scale deployment, techno-economic assessment, emission monitoring, and life cycle analysis, these are all essential to evaluate sustainability and scalability. Among the various treatment options available for managing nitrogen-rich agricultural effluents, the nitrification-denitrification process stands out as a key biological approach for the effective removal of nitrogen compounds, particularly ammonium and nitrate, from liquid waste streams, especially from digestate. The treatment relies on the coordinated activity of various microbial populations that degrade organic compounds, converting them partly into simple substances such as water, carbon dioxide, nitrogen, and methane, and partly into new microbial biomass. The simple compounds re-enter the natural biogeochemical cycles, while the excess biomass, along with the cellular debris and inert materials in the wastewater, is removed through sedimentation as an excess sludge. The nitro-denitro treatment plant can thus be considered an artificial ecosystem where the breakdown of biodegradable substances occurs through mechanisms similar to those in natural water bodies, though significantly accelerated and with much higher efficiency. Within this system, bacteria play the dominant role in purification, followed by protozoa. The composition and coexistence of microbial species within the biological reactor are shaped by natural selection, driven by prevailing environmental conditions. So nitrogen exists in the environment in both organic form, such as proteins, and inorganic form, such as ammonia or atmospheric diatomic nitrogen and nitrates, which are common in soils. In water bodies, ammonifying bacteria hydrolyze proteins and amino acids from decomposing biomass and animal waste, releasing ammonia, urea, uric acid, CO2, and water. While ammonifying bacteria is responsible for protein hydrolysis, nitrifying bacteria converts ammonia into less harmful forms. The biological removal of nitrogen involves two primary processes: nitrification, which oxidizes ammonia to nitrate, and denitrification, which reduces nitrate to molecular nitrogen. These transformations are governed by the type of bacteria involved in the process and by the environmental conditions under which they operate. Nitrification occurs mainly by some chemolithotrophic bacteria. For them, inorganic carbon is the only source of carbon, and the energy necessary for their growth and maintenance derives from the oxidation of ammonia to nitrate and nitrate. Denitrification, on the other hand, is the biological reduction of nitric nitrogen to gaseous nitrogen by chemorganotrophic bacteria that use nitrate instead of oxygen as the final electron acceptor. The nitrification is the biological oxidation of ammonium into nitrate through two steps. First, specific bacteria such as Nitrosomonas convert ammonium into nitrate. Then, other bacteria like Nitrobacter or Nitrospira transform nitrate into nitrate. This process occurs in aerobic conditions, meaning oxygen must be present. It also requires a neutral to slightly alkaline pH and moderate temperatures to keep the microorganism active. During nitrification, the bacteria consume oxygen and produce acidity, so the pH control and the aeration are very important. In manure and slurry treatment, this step converts the toxic ammonium into a form that can be biologically removed, reducing odor and nitrogen load in the next stage. The denitrification is the biological reduction of nitrate to nitrogen gas, which is safely released into the atmosphere. It happens in anoxic conditions where there is no oxygen available but nitrates are present. In this phase, bacteria such as Pseudomonas and Paracoccus use the nitrate as an oxygen source and need an organic carbon source like biodegradable chemically oxygen demand from manure to grow. The process removes nitrogen completely from the water, preventing eutrophication when the treated effluent is released into the environment. When managed correctly, nitrification and denitrification together can remove over 90% of nitrogen from manure or slurry, ensuring environmental protection and compliance with regulations. All biological nitrogen removal systems include an aerobic zone where nitrification occurs and an anaerobic zone where denitrification takes place, converting nitrogen compounds into gaseous nitrogen. Depending on the position of the anoxic tank relative to the aerobic one, three main configurations may exist. We have a pre-denitrification with the anoxic tank placed before the aerobic tank, or a simultaneous nitrification-denitrification system in which both processes occur in the same tank, or a post-denitrification with the anoxic tank located after the aerobic tank. In the pre-denitrification setup, the wastewater first enters the anoxic tank, followed by the aerobic tank. The nitrates from the aerobic stage are recirculated to the anoxic zone to enhance the denitrification. In the aerobic reactor, Remaining organic matter is removed and the ammonical nitrogen is oxidized. The treated mixture then passed to a settling tank where the biomass settles and it is partially recirculated to maintain the process. Excess sludge is periodically removed to prevent accumulation and maintain efficiency. When properly managed, this combined denitrification system can achieve over 90% nitrogen removal efficiency, while also ensuring high organic matter removal. Regarding the simultaneous denitrification processes, we can have SBR, sequencing batch reactor. These reactors are biological water treatment system with a discontinuous flow able of assembling the different process phases within a single reactor without requiring no type of recirculation. The peculiarity of this type of reactor is orienting the wastewater purification over time rather than space. The temporal sequence that distinguishes the SBR systems allows the duration of the times to be varied from time to time, according to the real needs of wastewater treatment. The discontinuity allows greater operational flexibility and strong control over bacterial selection, but, on the other hand, requires greater care in the management phase. It is obvious, however, that an inadequate design and management are the main factors that can determine the failure of this plant, whether continuous or discontinuous. The greatest advantages of the SBR reactor is hence to be able to make the most of what is instead a problem for continuous reactor, the variability of the input load. During the startup phase, it is possible to select a biomass adapted to different operating conditions, alternating periods of famine and abundance. Furthermore, during the management phase, it is possible to vary the phases of the cycle to favor a more efficient response to current conditions, in particular to a greater or lesser polluting load. It is precisely this alternation that discourages excessive formation of filamentous organisms for the benefit of bacterial communities able of performing nitrification, denitrification, and more extreme removals of phosphorus. Then we have the MBR plants. MBR stands for membrane biological reactor that are a combination of activated sludge processes with a membrane filtration system. So in these plants, the separation of the effluent from the biomass does not occur by sedimentation, but by filtration through the membrane itself. So depending on the nominal size of the pores and the molecular weight of the retained molecules, we speak about microfiltration or ultrafiltration. The driving force that allows filtration is the pressure gradient applied to the membrane between the side of the food and the side of the filtrate or the permeate. So usually, the microfiltration process operates at pressure not exceeding 0.7, 0.8 bar, while the ultrafiltration process operates at pressure usually between 1 and 10 bar. Membrane systems can also be differentiated from each other based on the geometry of the membrane used and the material used. This is an example of how the biogas technique could be applied in real application. The Groot Zevert Vergisting, located in Belgium, has implemented advanced nutrient recovery technologies to process pig slurry into bio-based fertilizer and clean water. Established in 2004, the GZV processes over 100,000 tons of pig slurry and agro-industrial organic waste annually through mesophilic digestion. In 2019, the facility announced its operation with two key nutrient recovery systems. The Genius, Green Engineering of Innovative and Upgraded Slurry technologies, focus on the liquid fraction of the digestate. It utilizes a sequence of physical separation and filtration technique. A decanter centrifuge separates solids from liquids, while a microfiltration and reverse osmosis further purify the liquid, concentrating the nitrogen and potassium. The end product is hence a nutrient-rich concentrate, and this concentrate is used as a renewable fertilizer, replacing synthetic alternatives. It's especially valuable because it can be locally applied, reducing the dependency on fossil fuel-based fertilizer and minimizing the environmental footprint of fertilization practices. The repeat system addresses the solid fraction of the digestate. It applies chemical precipitation and separation techniques to extract phosphorus. It produces struvite, that's magnesium ammonium phosphate, and calcium phosphate, both of which are stable, slow-release fertilizer. The phosphorus depleted organic residue can be safely reused as a soil amendment or soil conditioner. Oh, no. Turning agricultural residues into valuable products help transform waste from an environmental burden into a resource. By applying thermochemical processes like pyrolysis and biochemical methods such as anaerobic digestion or composting, it is possible to lower the greenhouse gas emissions, reduce reliance on synthetic fertilizer, and produce renewable energy. The resulting products, biofertilizer, biochar, animal feed additives, and bioactive extract, not only improve soil health and crop yields, but also open new revenue opportunities for farmers, reinforcing both sustainability and circular economy principles. Thank you and keep learning.